All right, everybody, this is the last lesson in our counting methods booklet. This is about combinations. So if you ever think of your locker, if you have a lock on your locker, we call it a combination lock. There's a combination that you have to put into it. But that's not actually combination, that's actually a permutation. Because when we talked about permutations, the order in which you put the numbers into your lock does matter. Now, the thing about combinations is that the order does not matter. We are just selecting, a group of people, but the order doesn't matter in which we're selecting them. So that's what the whole idea is behind combinations. And when it comes to like a quiz, a test, the exam, the questions are not going to say use the permutation formula, use the combination formula. You're going to have to pick out these keywords that will tell you whether it is a permutation or a combination. Okay, so for example, if we're selecting two letters, if we're selecting A and B, it is the same thing as selecting B and A. Those are not two different options. Whereas in permutations, if we have A and then B BA, the order of those letters did matter. So here the order does not matter. We are just picking things. There's this formula here for the combinations. So there might be a question that asks you to write it out as the formula. Is NCR, this is the notation, is equal to n factorial divided by r factorial, and then in brackets n minus r factorial. So the difference between the permutation formula and the combination formula is this r factorial here. This was not in the permutation formula, but it is in the combination. But the idea is still the same. We have n objects. We want to choose r of those objects. Using the TI-83, we don't have to worry about that. We are either going to be using our actual calculator or we are going to be using Desmos. So on Desmos, we write NCR, and then in brackets, we write what our n number is, and we write what our r number is. Now, I don't actually know if you put 9C3, like if you just type this, I'm not entirely sure if it will give you the answer or not. I've never actually tried it out. So maybe give it a shot with some of these examples that we do to see if that does work. The other thing is on these calculators that we have in class, there is an NCR button. So if we were to use that, it would just be, we would put the n number, and then we would press the NCR button, and then we would press whatever the r number is. So this is just how you would use one of our regular calculators to do it. So we're just going to run through some examples here and see how we use the combination formula and try to explain why they are a combination instead of a permutation. So example number 1 says there are 5 ice cream flavors to choose from. How many ways can 3 be selected if the order of selection does not matter? So we're just picking 3 out of the 5, but it doesn't matter which scoop goes where. Like one might be on the bottom, another one might be on top. The order does not actually matter. So we have 5 and we're choosing 3. So this is just 5C3. So we're going to do 5, and then we're going to press the NCR button, and then 3 equals 10. There are 10 different options. And that's pretty much all there is to it. Example number 2, how many ways can a committee of 3 people be chosen from a group of 6? So we have 6, we're choosing 3. I just want to point something out here too, is that you're going to see this word choose sometimes, or chosen. That is also a good indication of when we use combinations. So just something to look out for. So we have 6, we want to choose 3, so this is 6C3. And again, we're going to use the calculator. 6C3 is 20. Now, just seeing how we use the formula, if we were to do 6C3 using the formula, would be 6 factorial over 3 factorial and then 6 minus 3 factorial. And we can simplify what is inside the bracket. So the 3 factorial and 6 minus 3 is just 3. So that's another 3 factorial on the bottom. So if we were to just do this on the calculator, let's see what we get. So 6 factorial divided by, and my denominator, because I have two things in the denominator, I'm going to put it in brackets. So 3 factorial times 3 factorial, close bracket, you can see we still get 20. So this button is a nice shortcut, but if your calculator doesn't have that shortcut, or God forbid something happens to Desmos and it crashes one day, this is another way that you can solve it on the calculator. Example 3, a committee of 2 boys and 3 girls are being selected. This is another word here. So we said chosen. Selected is another one of those keywords that indicates combinations. So 2 boys and 3 girls is to be selected from a class of 15 boys and 18 girls. How many different committees can be formed? Well, we have 15 boys and we're choosing 2 of them. So 15C2. We have 18 girls and we're choosing 3 of them. But now, what do we do with these 2 different calculations? And there's another keyword, and this is going back to our very first lesson of this unit, is this word right here, and. So whenever we see the word and, that means we're going to multiply. So I'm going to do 15C2 times 18C3. So 15C2 times 18C3 is 85,680. Now I'm not entirely sure whether this is correct or not, so I'm going to actually double check by doing each of these calculations separately and then multiplying those answers together just to make sure. So 15C2 is 105, 18C3 is 816, and if I do 816 times 105, I did get 85,680. So, I mean, even for me right now, I wasn't necessarily confident, so it's always good to double check your work if you can. Now we have 2 more examples on the other side. Example 4, a planning. I think this is supposed to be maybe a planning committee. There's a word missing here. A planning committee is to be formed for a school-wide track meet. There are 13 volunteers, 8 teachers, and 5 students. How many ways can the principal choose a 4-person committee that has at least 1 teacher? So at least means there could be 1 teacher, there could be 2 teachers, 3 teachers, or 4 teachers. Okay, so let's kind of highlight the information that it's giving us. So we know that there are 13 people in total. 8 of them are teachers, 5 of them are students, and we want to make a 4-person committee. Now, there are 2 different ways that you can approach this problem. I'm going to go through the steps of the longer way first, and then I'm going to show the shorter way afterwards. So, if the committee has at least 1 teacher, that means that the rest of the committee would have to be 3 students. Another option is we could have 2 teachers and 2 students. We could have 3 teachers and 1 student, or we could have 4 teachers and 0 students. So we could do the calculations for each of these. So 1 teacher, 3 students. Well, we have 8 teachers, we want to choose 1. So 8C1 times 5 students, we want to choose 3, 5C3. 2 teachers and 2 students would be 8C2 times 5C2. 3 teachers, 1 student, 8C1, 8C3 times 5C1. Or we could have 8C4 times 5C0. Also, just one thing that I want to point out, not really related to this. Whenever you have something C0 or something C something, so like 5C5, if these numbers are the same, both of those always equal 1. So just to show you here, if I do 5C0 equals 1, because there's only one way we can choose nothing from a group of 5. And if we're choosing 5 from a group of 5, well, there's only one way that I can choose everybody from that group of 5. So just something to point out. Anyways, we're going to run through these calculations here very quickly. You can do them yourself as well, and we'll jump back into it and look at the shorter way after. All right, so I did the 4 calculations here. The first one gave me 80, then 280, then 280, and then 70. So to find the total number of possibilities, we just add those 4 numbers together to get the total. There are 710 possible committees that have at least one teacher. But this is a really long way because we had to do 4 calculations for it. So there is a bit of a shortcut, and the shortcut is we take the total number of ways with no restrictions, and we're going to subtract the number of committees with 0 teachers. Because when we subtract that, we're going to be left with all the options from the total that have at least one teacher from it. So when we do this calculation, the total number of committees, if we're just not restricting anything, well, there are 13 people in total, and we want to choose 4 of them. The committees with 0 teachers means I'm going to have 8 teachers and I'm choosing 0, times 5 students and I'm choosing 4 of them. And when we do this calculation, we should also end up with 710. So if I do 13C4 is 715. And if I do 8C0 times 5C4 gives me 5. So when I do 715 minus 5, that still gives me the same answer. Okay, so this is a bit of a shortcut. You can do each of the individual calculations. It's 100% going to be correct. But just know that there is another way that you can approach this problem. And especially when we get into the probability unit, this shortcut is probably going to be the faster way to do it. But we're going to worry about that in the next unit. We have one more example here, example 5, talking about cribbage. So a cribbage hand consists of 6 cards. We have 52 cards in a deck, 4 different suits of 13 cards each, so 4 aces, 4 twos, 4 threes, blah, 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 all the way up to 4 kings. How many different hands are possible? So this is just no restrictions whatsoever. It's a very straightforward question. We have 52 cards. We're choosing 6 of them in a hand. The order of the cards that we're taking doesn't matter. We have 6 cards in our hand. So there are, look at that, 20,358,520 possible hands that you could have in your cribbage hand. How many have exactly 3 kings? Okay, so now we're starting to put some restrictions on things, just like we did in the previous question where we were restricting to the amount of teachers. In this one, we're restricting to the amount of whatever. In this case, it's kings. So what this means is we're going to have 3 kings and we're going to have 3 other cards that are not kings. Okay, because it's going to be exactly 3. Okay, so 3 kings. Well, there are 4 kings in a deck of cards. So we have 4 kings. We're choosing 3 of them. And again, it's not explicitly stated here, but we have 3 kings and we have 3 other cards. So we're going to multiply that. We know that we're choosing 3 other cards. But now how many other cards are there in the deck? Well, we're taking all of the kings out. So we had 52 to start. When we take out those 4 kings, we have 48 cards left over. So this is going to be 4 choose 3 times 48 choose 3. So I'm going to do 4 choose 3 times 48 choose 3. There we go. Is 69,184. Okay, again, seems like a large amount, but if you were to actually go through all of the different hand combinations, it's really not that far-fetched. And then part C says how many will have no face cards. So again, a face card is a jack, a queen, or a king. So we are removing those cards, and keep in mind there are 4 of each. So we are removing 12 cards total. So if we're taking out 12 cards from 52, that means we have 40 cards left over. We're choosing 6 of them. So this is going to be 40 choose 6 is 3,838,380. Do you think it's a coincidence that these numbers go 383838? I don't actually know. I just thought that was kind of interesting. But yeah, so that does it for combinations. So again, there aren't going to be questions that are going to tell you to say use permutations or use combinations. So make sure that you understand permutations is when the order of something does matter. Combinations is when the order doesn't matter. We're just choosing them. We're just selecting something. But the order in which we select them does not matter.